All right, dude, we are live. What's up, guys? This is Dem Keys, and today we're gonna continue learning. Um, we're I, you know, ever since we started this new activity, I have not managed to pick a good intro for this, so I'm just gonna say that today we're gonna continue doing ESP32 things and Rust things. Because I mean, technically, yeah, we are doing that. Give me a sec. Okay. Sorry. I got busy with something. What was I saying? Yeah. Um, what's up, guys? Today we are gonna be doing more ESP32 things and more Rust things. And I've been doing more research on basically how various components of microcontroller circuits work, how various not components necessarily, but various concepts within digital electronics work. That whole thing about floating pins and the need for pull up and pull down resistors and how voltage dividers are working and a bunch of like similar concepts, because I've always had this issue where I need to go down to the lower level to try and understand things. And when I try to do that here, because of my lack of advanced analog electronics knowledge, I find myself having to do research on the analog part first, to learn that part first, and then I can understand this digital part that I'm trying to understand. Because of which, I'm losing a lot of time, and so I decided to sort of um, refocus or change my focus or change my way of approaching this research in such a way that I'm mainly focusing on the digital side rather than trying to go down to the analog side or go down to the analog level. Um, and I would prefer to remain on the digital level unless we absolutely need to go down to the analog level. There will be select few situations where that is necessary, and of course, if we are actually doing analog stuff like reading analog signals or writing analog signals, then yeah, we do need to go down to the analog level and understand things on the analog level, which is fine for those specific situations. Yeah, we can do that. There's also, some base analog electronics knowledge that is necessary, which fortunately I already have that, because I have very basic analog electronics knowledge, simple enough that I can set up a very simple, battery circuit or even microcontroller circuit and do voltage and current calculations. So I have like very, very, very basic analog electronics knowledge, and I intend to expand that as well over time. It's just that right now, as of right now, I don't have very high analog electronics knowledge, and that kind of clashes with my need to try and understand things on a much lower level, and that's why I'm trying my best to stick to the higher level. So I've been having a very long conversation with Gemini about trying to understand um, how these different concepts within digital electronics work, but on a higher level. And also, I tried to get Gemini to basically teach me about digital electronics, because something that I realized is that while I did explore and get started with digital electronics, I never actually I never actually took the I never actually how do I say this? I never actually read up on something that is explaining how digital electronics works and how what are the concepts within digital electronics. The only way that I learned about the various concepts in digital electronics was by going through the various examples within the Arduino library, or well, within Arduino. And this is why products like Arduino, platforms like Arduino, are incredibly useful for getting people started in digital electronics, because they introduce you to these concepts. They have a full-fledged IDE. They have built-in examples. They have within that IDE, of course, you have the compiler. Um, you have a serial monitor as well. Through the serial monitor, you can do serial read and serial write. There's a whole like, it's a perfect learning environment for you over there. And through that, I don't know about doing advanced stuff, but you'll definitely be able to take your first steps into digital electronics, and you'll be able to learn about working with microcontrollers through that. It'll give you a fairly decent introduction to various digital electronics related concepts. Um, why was I talking about this? I started appreciating Arduino and then just forgot what I was talking about. Well, anyways, so I was having this conversation with Gemini because yesterday I realized, as I was continuing the previous conversation that I was having with Gemini about um what do you call it? Um Sorry, there's somebody who's riding their bike outside and their brakes are squeaky as hell. Okay, the person's wow. The person's off in the distance and I can still hear the weird squeaking sound. Okay, anyways. Um what was what was I saying? Yeah, so after yesterday's stream, I was continuing the conversation that I was having with Gemini. I was trying to understand, all. I was trying to. Okay, so I first of all, what I had to have a conversation with Gemini about was, hey, I have this very limited analog electronics knowledge, right? I have somewhat okay digital electronics knowledge. I do have the willingness to learn. I want to learn. I want to understand how things work on the lower level. My problem is sometimes I start going too deep into it, to the point that it goes down to the analog electronics level. And then I end up spending a lot of time doing research on various things, because once I go down to that level, I'm introduced to concepts of advanced analog electronics, which I don't know. So, is there anything that you can tell me that's going to sort of put things into perspective for me and make me understand that, hey, it's okay to be on the higher level for a lot of the stuff? You don't always need to go to the lower level. And so Gemini sort of um, laid out the information for me and gave me some good advice on it. And yeah, yeah. So after that, now I'm going to be focusing on just doing the digital level stuff. And in terms of understanding how things are working, I am okay with letting certain things be considered black box, and not going too deep into it, even though I can, but still not going too deep into it, just so I don't end up wasting a lot of time. What else? What else? I'm very close to basically being, there's just these various questions that I have because I'm now considering it as a black box technology rather than trying to go deeper into it. So now I want to ask all these various questions that, hey, and this is just one example. Like, hey, how is it that I'm able to connect? How is it that I'm able to connect a resistor from VCC to ground, and the microcontroller isn't harmed, and even the resistor itself is not harmed? How is it that I'm able to likewise connect a potentiometer, which is a variable resistor? How am I able to connect that to how am I able to connect that between VCC and ground, and then take one connection into one of the ADC pins so I can read like signals from it? And how is nothing getting damaged? I need to understand all this, and this is where like I've paused the conversation that I've been having with Gemini, and I'm gonna keep it paused. I'm not gonna read it out on stream. That's for research off stream, but I'm getting there in terms of building my understanding of doing things and how things work in the digital side of electronics. Okay, so wait, is there disturbance coming through? Hold on, I need to check this because I'm noticing the thing in my OBS in the volume meter. Check, check, testing, testing. Hello, hello. Check, check, testing, testing. Nah, we're good. We're good. All right. Now, so what are we doing? So I was having the conversation with Gemini. Like I mentioned, I'm not gonna go too deep into that here. I do want to get started with doing with actually doing, some sort of project. I am gonna start with a simple question. Hey, I'm doing ESP32 no STD Rust projects, or I should say ESP32 projects using no STD Rust. Um, I I have to set up a circuit where I connect. Oh, where I a circuit with a potentiometer where I connect pin 1 to VCC, pin 2 to ADC, and pin 3 to GND. After that, I need to write some code to read the signal coming in from the pot. What I'm wondering is this circuit safe, or is there, or are there any things I need to alter or take into account? Because I just want to be sure that, hey, this circuit that I'm building, this is perfectly fine. Do not use the thinking mode. Hold on. Actually, maybe we should use the thinking mode for this, but I don't want to spend my tokens for this. Well, okay, I'll use it. Okay, assessing circuit safety. All right, this is a classic setup, but with the ESP32, there are a few gotchas that can mean the difference between a working project and a puff of blue smoke. The short answer, the short answer, it is safe as long as VCC is 3.3 volts. If you connect that VCC pin to a 5-volt rail, often labeled VIN or 5 volts on dev boards, you are risking frying the ADC pin. Oh, the ADC. Okay, okay. Yeah. Okay, yeah, that makes sense. That makes sense. That's definitely something good to take into account because on the Arduino, I don't think we would have this issue. On the Arduino, I believe it all works at 5 volts. I don't know if they ever changed that, but I believe it all works on 5 volts. I think so because Arduino Unos, they're like beginner boards, right? You probably don't want to introduce um, the added complexity of differentiating between the voltage that the dev board takes and the voltage that the pins operate at. I could be wrong. I should look that up at some point. I don't do Arduino Uno stuff anymore. I don't plan on doing Arduino Uno stuff because I'm using ESP32, so I have no reason to do Arduino Uno stuff. But yeah, yeah, out of curiosity, I should look that up. Okay, the 3.3 volt golden rule. The ESP32 is not 5 volt tolerant on its GPIO pins. True, true. I do remember that. Um, if you hook the potentiometer up to 5 volts, when you turn the knob all the way to the max, you'll be sending 5 volts directly into a pin rated for 3.3 volts. Okay, ensure pin 1 of your potentiometer is connected to the 3.3 volt pin on the ESP32. Okay. Actually, let me look at my board real quick. Okay, so the good news is the 3.3 volt pin is on the side that I have access to. Yeah, yeah. It's on the side that I have access to. And V in, which I'm assuming is going to be 5 volts, that is on the other side, the side that I don't have access to. Give me a second. Let me put the board back. Yeah, so if you look at the board right now, the bottom side of the board, the lower side of the board, is what um, it, I have access to those pins. I don't have access to the pins that are on the upper side. And that's mainly because of the breadboard that I've put this on, because the thing that I've put it into is pretty narrow, and that's why I'm not able to, you know, use both sides. Though this has me curious about something. I wonder if I can like measure it right now, real quick, because when I placed so I've placed the microcontroller here, right? I need to be careful to not. Wait, can you guys see the screwdriver? Oh, there's crazy latency, dude. What is that? Okay. All right. Well, whatever. So if you look here, the board is here, right? The way that I've placed the board, I only have access to, maybe you guys can't see it, but where these jumpers are connected, that's a row over here above this blue line. I don't know if the blue line is also visible or not, but like this is a blue line, this is a red line. Um, these are basically just rails that run like that, and usually you're supposed to connect this into power. So your VCC and ground would go into these rails. It's just out of convention. You can plug whatever you want to into it. You're not obligated to specifically plug power related stuff into it. For example, if you look on this side, on the far end, let's say the bottom right of the breadboard, I've placed what is it called? I forgot what this was called. It's a light what is it? Light determined resistor? No, light. Hold on. LDR resistor. Light dependent. Is that what I said? Light dependent? I think I said light dependent. So yeah, this is in it's an LDR. It's a light dependent resistor. Basically, the more light you give it, the lower its resistance is, and the lesser light it receives, the higher its resistance is going to be. And apparently, its resistance is usually in, like, I don't know, the mega ohms. I don't know how much this specific one is, but like at least according to Gemini, it's in the mega ohms. Which is, I mean, in my case, if it even happens to be in like uh the kilo ohms range, or hundreds of kilo ohms, that's still perfectly fine for me. Anyways, the point is, um, what I did here is I put so this is a good example of how you could use these rails for different purposes. You're not limited to just using them for power, even though conventionally they are used for that purpose. In this specific instance, I needed some space, so I could like bring my hand like this to cover the sensor itself, cover the resistor, because that's how I would test for that's how I would test whether it was working or not. In fact, I could change the connection real quick and show you guys the thing working right now. Okay, so if you look at the thing right now, if I bring my hand over and cover the sensor, the red light is going to get dimmer. Yeah, I hope that was visible well enough on stream. I think so. Yeah. So this is a good example of how you can use these rails in different ways. Um, okay, so what is next? Oh yeah, I was having this conversation with Gemini. I still haven't done the voltage divider calculation. I need to do this voltage divider calculation um, determine determine what the actually no. You know what? Hold on. So how am I determining this? How exactly am I determining this if so this is a voltage divider, right? This is a wait, hold on. So this is a voltage divider, right? This is um this is a voltage divider. However, this is a variable resistor. This is a potentiometer. It's not just two solid resistors, you know, creating a voltage divider. Yeah, it's not two solid resistors creating a voltage divider. It's um, it's a potentiometer, but like we treat it as a voltage divider because of the way that it functions. And depending on where the wiper is currently at, the ratio between these two resistors, like we can consider them two separate resistors that are connected together. Depending on where the wiper is, the ratio determines the resistance on one side and on the other side. And that's what we are going to be calling our R2 and R1. So the formula that we are supposed to be using here is, hold on, let me go to Python. The formula is, actually, maybe we can make this a function. Def pot R1, R2. We can also do V in. Okay, and then we are going to return, let's group this. We are going to return R2, is that what it is? Yeah, R2 divided by R1 plus R2 multiplied by, yeah, R1 plus R2 multiplied by V in. So that's what we are supposed to be returning. Okay, now keeping that in mind, let's call this function. So our V in, we're going to say 3.3. Our R is, let's say, 5,000, and the other R is also 5,000. What's this giving us? 1.65 volts. Okay, if we shift, should I make like a function that calculates the ratio as well? That sort of, maybe I could vibe code it so I don't have to sit here and figure out the math for. Okay, no, never mind. So let's say we are at 25%. Okay, 25% on R1 is gonna mean between VCC and the pin, we have a resistance of 2,500 ohms, but between the ADC, that's the pin, and ground, we have a resistance of 7,500 ohms. What does that do? That increases the voltage, right? What happens if we switch this? That's going to decrease the voltage. Okay, now that being said, what's being measured here is apparently the voltage, or is it the current? No, we have the voltage, but the current is low enough that we are able to measure this voltage. This brings up an interesting question that I should ask Gemini later on. Maybe I can note it down for now. Perhaps I should note this down in here. Post stream notes. Ask Gemini. Potentiometer. Pin 1 connected to, no, wait, okay. Potentiometer connected to VCC, ADC, and GND. As the pot turns, resistance changes on both sides, meaning voltage being read by the ADC changes. Wait, changes. Hold on, there's something to be looked at here as well. So if we are using okay, I equals V divided by R, right? So if we say low resistance, that's our voltage, right? Let's say 2.475. So 2.475 V divided by R, 2.475 divided by 2,500. So we are now at 0.0001. Actually, that's about to become 0.001 amps. Let's multiply that by 1,000. Is that correct? I don't think that's correct. I don't think that's correct. Hold on. Amps to milliamps. Yeah, we multiplied by 1,000, right? So if we say 0.00099, oh yeah, that is correct, because what I'm looking at is milliamps. My bad, my bad. Okay, so we are sending in around one milliamp. We are sending 1 milliamp into the ADC. Okay, all right. So now this brings me to my question here. Voltage being read by the ADC changes. Well, okay. Voltage, not just read, let's say into, fed into the ADC changes. Voltage and current being fed into the ADC changes. Could this be bad somehow? That's our question. So I'm going to ask that later on to Gemini. Let's go back. Okay. Now, what was the remainder of the conversation? ADC attenuation. So I'm guessing this is about the calibration, which we can. Okay, yeah, we'll read this. We'll read this and see how to go about approaching that. Right. So in no STD Rust, likely using ESP-HAL, you'll notice that the ADC doesn't read 0 to 3.3 volts by default. The ESP32's ADC uses an internal reference voltage, usually around 1.1 volt. To read higher voltages, you have to configure attenuation. Okay. If you are using a 3.3 volt supply for the pot, you must set your attenuation to 11 dB or 12 dB in your Rust code, or your readings will flatline at the maximum value long before you finish turning the knob. Okay, let's see how to do that. ESP32, no STD, Rust, attenuation. Give me a second here. What was I gonna do? I was gonna do something. I can't remember what. Oh yeah, I just remembered. Yeah, give me a second. Okay, all right. Where was I? Actually, hold on. Oh God, dude, I need to be so careful with this. All right. Huh. Okay. Right. So we were um discussing. Oh yeah, attenuation. I was looking that up. Do I need to though? Do I need to do any attenuation for this? Maybe I actually don't even know which crate I would be looking for. Yeah, I'm not sure which crate I would be looking for. Um oh, here it is. Yeah, 80 so okay, somehow it didn't occur to me that ADC the attenuation is for the ADC, and so I should probably look in the ADC crate or the ADC module of the ESP HAL crate. Okay, so we have attenuation here. Um, we are able to, okay, so the approximate attenuation of the ADC pin. Oh, hold on. Does this mean we can set yes, we can set the attenuation when we enable the pin. And I guess that solves that attenuation problem for us. And we can also change it if the attenuation happens to be inaccurate or yeah, inaccurate is the best. Uh, I was about to say inaccurate or wrong, but like, same thing. Um, just a second. All right. Okay. Cool. Now, um, if you are using a 3.3 volt supply, wait, so what is attenuation for exactly? Like, the ESP32 ADC uses an internal reference voltage, usually around 1.1 volt. To read higher voltages, you have to configure attenuation. Okay, so 0 dB is around 1.1 volt, 2.5 dB is up to around 1.5 volts, 6 dB is up to around 2.2 volts, and 11 dB, often called 12 dB, reads up to around 3.3 volts. That's why I have to set it to 3.3 volts or to 11 dB. But I kind of want to get an understanding of why exactly this is. Okay, so um, I'm doing ESP32 projects using no underscore std rust. When I try to use a pot with, when I try to use a pot to read to what? When I try to use the ADC to read a pot's signal, I've been told to set the attenuation to around 11 dB if um, if pin 1 of the pot is connected to VCC, VCC, which is 3.3 V. Help me understand why. Okay, working with no STD Rust on an ESP32 is a bold move. It's efficient, but as you've discovered, it forces you to face the hardware's quirks head on. I'm realizing that. Yes, I'm definitely noticing much more of the implementation details being exposed to me compared to when I was using MicroPython. Because with MicroPython, there's like a shitload of high level stuff going on. And that's a good thing because you don't always want to be exposed to these implementation details and have to set implementation details manually. Though there are specific situations, even within MicroPython, like when you're using MicroPython, where you would need to set details, you would need to set the specific implementation details. But the reason there is not it well, there is a reason. It's not for no reason that you have to set these extra details. You would usually only need to set it if ambiguity wasn't a good thing there. So if setting, or rather, if setting a default value wasn't always the best idea. So if there's a specific situation where a certain variable's value could be one of a set of values, but you don't necessarily know which value out of them is the most commonly used one, then you would just let the user set it, because it's much better to just allow them to set it rather than keep a default and then the user has to change it later on, or maybe there might be some confusion because that implementation detail has been hidden away. But yeah, okay, back to this. I kind of like that this stuff is being exposed to me, because it's giving me a chance to learn things on like a lower level. Okay, the short answer: the ESP32's internal ADC is actually quite fragile when it comes to voltage. Okay, left to its own devices, it can only quote unquote see signals up to about 1.1 volt. Since your potentiometer is swinging all the way up to 3.3 volts, you have to use an internal attenuator to shrink that signal so the ADC can understand it. Okay, okay. The one the 1.1 volt ceiling. The ESP32 uses an internal reference voltage of approximately 1.1 volt. At 0 dB attenuation, which is the default, the ADC can only measure voltages between 0 volt and 1.1 volt. The problem, if you hook up a 3.3 volt potentiometer without attenuation, the ADC will hit its maximum. That was going to be my next question, that is this a risk of damage, or is it just the fact that it's going to hit that ceiling pretty quickly and then just remain there? So like if we are if we if the range here is meant to be 0 volts to 1.1 volt, or 0 volt to 1.1 volt, and we are going past that, and this range, by the way, is then meant to be translated to a range between 0 and 4095, then is it possible that when we try to use a range of 0 volts to 3.3 volts on this pin that is configured to do 0 volts to 1.1 volt, it's going to keep going? Or rather, how do I say this? The I need to kind of visualize this for you guys. So where should I do this? Let's do it in NeoVim. I believe I opened up a Scratch thing. Did I? I don't remember. I don't think I did. Oh, I probably didn't even have a Scratch thing here. Okay, we can create a new Scratch thing. Scratch 01 and then save it. Okay. So what I'm wondering is, if we have a pin that is meant to read, I'm going to make 10 things here, okay? So let's say 0, 0, 0, 0, 0, 0. Actually, would tab be respected here? Yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And let's say this range is 0 to 4095. This is our range, right? And let's say we let's say this is supposed to be 0 volts, right? And then once we go here, this is supposed to be 1.1 volt. So is it possible that if we try to use this scale, essentially, that we have this scale that is limited to this range, if we try to apply, hold on, so we are saying 3.3 volts, right? Let's make that there. Could this be what's going to happen? Like, we have 3.3 volts all the way up to the end there, right? And if we try to use that with this, could it be that we will hit 4095 pretty quickly over here? Yeah, could it be that we'll hit 4095 pretty quickly once we hit 1.1 volt, and then anything above that is just, it's just not going to be counted? Anything above that is just going to be 4095. I'm curious if that's going to be the case here. Let's see. The problem, if you hook up a 3.3 volt potentiometer without attenuation, the ADC will hit its maximum value, which is 4095 in 12-bit mode. as soon as the pot reaches 1.1 volt. Okay, that's exactly what I was thinking. Actually, I wasn't able to put that into words for some reason. This thing about the pot touching 1.1 volt, I wasn't able to like explain that that's what I was talking about. That's why I had to like draw out the entire like scale. Okay, the remaining two-thirds of your knob's rotation will just return the same maximum value. It's like trying to measure a 6-foot person with a 2-foot ruler. Okay, how attenuation fixes this? Internal to the ESP32, there's a programmable resistor network, an attenuator, that that acts like a volume knob for incoming voltage. It scales the input down before it hits the actual ADC circuitry. Okay, why specifically 11 dB? The term 11 dB refers to the logarithmic. I was actually curious about this as well. Why 11 dB? It refers to the logarithmic reduction of the signal power. In terms of voltage, 11 dB provides a reduction factor of roughly 3.55x. So 3.9 volts divided by 3.55 is around 1.1 volt. By setting it to 11 dB, you are telling the ESP32 to squeeze 3.3 volts tends to flatten out. Okay, okay. I'm gonna be honest. I think that's happening with this potentiometer, even without um, a microcontroller being involved. So I think I've already been dealing with that. Okay, all right. If you need high precision, you usually have to apply a calibration curve. Then the 3.3 volt versus 3.9 volt limit. While 11 dB technically allows the ADC to read up to 3.9 volts, the ESP32 pins themselves are only rated for around 3.6. Since your pot is at 3.3 volts, you are perfectly safe, but you'll notice the ADC is most accurate between 0.1 volt and 3.11 volt. In Rust, make sure you are using the add config or similar peripheral traits to set the attenuation. Okay, yeah, we actually have that mentioned here. Add config and then add config.enable pin, so and so. Okay, one last thing. Do I need to worry about the amount of voltage slash current going to the ADC given my setup as I turn the knob to either side? Okay, the short answer is in your current setup, you're safe. Since your potentiometer is powered by the same 3.3 volt that powers the ESP32, you aren't at risk of blowing the pin. However, there are three specific things you should understand about what's happening electrically when you turn that knob. Voltage limits, the safety zone. The most important rule for the ESP32 GPIO pins is that the voltage should never exceed VDD plus 0.3 volts. If your ESP32 is running on 3.3 volts, the maximum safe voltage is about, oh, that's what VDD is. Whatever the microcontroller is officially running at, or whatever its max voltage is. Okay, so the maximum safe voltage In that case, if VDD is 3.3 volts, then the max safe voltage here is 3.6 volts. Since your potentiometer's high side is connected to 3.3 volts, the wiper, which is the middle pin, can only output between 0 volts and 3.3 volts. You are well within the safe zone. If you were powering the pot with 5 volts, you would definitely need a voltage divider to protect the ESP32, as 5 volts would likely damage the silicon. All right. Then current, the high impedance shield. You might worry that turning the knob to the 3.3 volt side will shove too much current. I actually was worried about that. And then I did the, I equals V divided by R calculation. Basically, I did the current calculation, and it's 1 milliamp. Okay, yeah, let's continue reading this. Fortunately, an ADC pin is high impedance. Think of the ADC pin like a person holding a voltmeter against a wire. The person isn't consuming the electricity, they are just looking at the pressure. Internally, the ADC has a very high resistance, typically in the mega ohm range. According to Ohm's law, because R is massive. Oh, okay. I was calculating. I wasn't considering the the impedance of the pin. I was considering the resistance in the potentiometer itself. But okay, let's see what Gemini is saying. Okay, because R is massive, the current flowing into the pin is microscopic, picoamps or nanoamps. I should ask that question next. Okay, then the dead zone at the ends. While you don't need to worry about damage, you should worry about accuracy at the end of the knob's rotation. Even with 11 dB attenuation, the ESP32 ADC is not rail to rail. The bottom end, below 0.1 volt, the ADC often reads flat 0, and the top end, above 3.3 volts, the ADC above 3.1 volts or 3.2 volts, depending on the specific chip. The ADC often saturates and reads the maximum value before the knob actually hits the end. You know what? This seems to me like here I would need to do my own attenuation. So I would then need to kind of, I guess this counts as recalibration of my own. So I would have to change the range to be, if I know that there's a dead zone below 0.1 volt, or let's make it higher. If I know that there's a dead zone between 0.5 volts, did I say between or below? I meant below. If I know that there's a dead zone below 0.5 volts and there's a dead zone above 3 volts, right? What I could do is I could remap the range to be not 0 to 3.3, but rather 0.5 to 3. So I would then remap what was 0 volts to 3.3 volts to 0.5 volts to, or let me say that again. I could remap what was going from 0 volts to 3.3 volts. I could remap that to go from 0.5 volts to 3 volts. Right. So then previously where 0 volts to 3.3 volts was being translated to a value between 0 and 4095, now 0.5 volts to 3 volts is going to be translated from 0 to 4095. So everything below 0.5 volts is just going to be ignored, and everything above 3 volts is going to be ignored. So this way, we have a more accurate reading, we have a more accurate range. Though it's worth noting that this is, I don't know if that's gonna, I don't know why I was thinking about this initially. Like what did I think, what problem did I think this was gonna solve? Um, yeah, I don't know what problem I thought this was gonna solve, because physically when you keep turning the thing, physically when you keep turning the thing, if you're, let's say, at the low end and you've set 0.5 volts to be your starting point, right? You're going to have to turn the knob a little bit with just nothing happening, no response, until you hit 0.5 volts. So that becomes the dead zone. You still have to like turn within that dead zone, and then you have like that awkward kind of thing going on. It's going to be a little more accurate though, that's for sure. It's going to be accurately mapped from the range that is actually working to another range that's actually working. But then is that really, isn't that the same thing? Hold on. That's, I feel like that's doing the exact same thing. If below 0.5 volts we just flatline, we're accomplishing the exact same thing. So then we are doing all this work for nothing. Yeah, that's, yeah, that was silly. Um, we do not need to do that because that's not solving the problem. That's recreating the exact same problem. Why did I think that was going to do something? I don't know. Okay, okay. Right. Um oh, yeah, wait. Okay, if you notice that the last 5% of your knob's rotation doesn't change the value in your Rust code, don't worry, your hardware isn't broken. It's just a limitation of the ESP32's internal ADC design. Okay, so I didn't take the pin's um, own impedance into account. Um, when I was doing the I equals V divided by R calculation, I calculated using um, using using VCC and R. So we've um, assuming we are at 0% and we've turned the knob 25%, we would be looking at 2,500 ohms. So I did 3.3 volts divided by 2,500. Help me understand if this calculation was accurate, inaccurate, or even incomplete, considering I didn't take the pin's impedance into account. Okay, we're gonna learn something here. Okay, this is a very common point of confusion when first diving into hardware. Your calculation is incomplete because it confuses current flowing through the potentiometer with current flowing into the ESP32. In electronics, we have to look at two different paths for the electricity. The main path, which is through the pot, when you connect pin 1 to 3.3 volts and pin 3 to ground, you've created a constant path for the current. If you have a 10K ohm potentiometer, the current flowing from VCC to ground is 0.33 milliamps, okay? Because it's 3.3 volts divided by 10,000. Awesome. Then this current flows through the resistive track of the pot regardless of whether the knob is turned. Sorry, zoned out. Okay. Regardless of whether the knob is turned. Your calculation of 3.3 volts to divided by 2500 ohms would only be true if you were measuring the current from the 3.3 volts rail through just a 2.5 ohm chunk of the pot directly to ground. Okay, the branch path into the ADC. The ADC pin is a branch off the main path. The ADC pin is a branch off the main path. To calculate the current going into the ESP32, you have to use the resistance of the ADC pin itself, not the resistance of the potentiometer. As we mentioned before, the ADC input impedance is extremely high, typically around 10 mega ohms, which is 10 million ohms or more for the ESP32. If your knob turned, if your knob is turned so the wiper is outputting 3.3 volts, the current entering the pin would be 3.3 volts divided by 10 million ohms, which is 0.00000033 amps. That is 330 nanoamps. That's tiny. Okay. Because the pin's resistance is so much higher than the potentiometer's resistance, the ADC is invisible to the circuit. It doesn't load the circuit or pull enough current to change the voltage you're trying to measure. Where your calculation does matter, source impedance. While you don't need to worry about damaging the pin with current, your calculation relates to something called source impedance. The ESP32 ADC works by changing a tiny internal capacitor, sample and hold. If the resistance of your potentiometer is too high, example using a 1 mega ohm pot instead of a 10K pot, the trickle of hold on. Doesn't this mean I could directly connect VCC to the ADC without damaging the ESP32 or specifically damaging the ADC pin? Doesn't this mean I could technically connect the thing in that way? I think so. Yeah, I think so. Let me check. But yeah, let me continue reading this. Uh okay, if the resistance of your potentiometer is too high, example using a 1 mega ohm pot instead of a 10K pot, the trickle of current isn't fast enough to charge the internal capacitor reads before the ADC takes its readings. Your 10K pot is perfect, the source impedance is low enough to charge the ADC's internal guts almost instantly. A 1 mega ohm pot would get very jumpy, inaccurate readings because the current can't keep up with the ADC's sampling speed. The verdict, your math was looking at the resistance of the source, which is the pot, but your safety slash current draw, but for safety slash current draw into the chip, you must look at the resistance of the load, which is the ADC pin. In your Rust projects, in your no STD Rust projects, you can rest easy knowing that as long as the voltage is 3.3 volts, the current will naturally stay at safe microscopic levels. Okay, so I'm a bit confused here. In your 3.3 divided by 10 million calculation, you didn't take the 2500 into account. The 2500, assuming the knob is turned 25% into account. Why is that? Isn't 3.3V going through about 25% of that 10K ohm resistance before getting to the pin? I feel like this is where I might be, this is where my not so great understanding of voltage versus current might become a problem. I think so. I think so, because I have had this issue in the past as well, where it was like, okay, how much voltage is going in? If the source voltage was something, am I really changing the voltage that's going in, or am I changing the current that's going in? Like, for example, a resistor is known as a current limiting device. It's used to limit the current. But then when you apply that limited current as an equation, um, I equals V divided by R, V equals IR. V equals IR. I forgot how I was getting to the point where the voltage also changes. I can't remember what that was, but there was a similar like situation. I'll mention it later on if it comes to me. Okay, this is a perfectly logical question. It feels like that 2500 ohms of resistance should be slowing down the voltage or current before it hits the pin. To understand why it doesn't change the voltage calculation much, we have to look at how a voltage divider, which is what a potentiometer is, actually works. Okay, you know what? This is giving me something to do research on. Okay. Um, however, hmm, you know what? Give me a second here. Um, Hold up, because here I might need to do a slightly different type of search. Actually, hold on just a second. Oh, okay. You know what? I am not sure. Yeah. I'm just gonna wait. Hold on. Is this person currently at their desk? I think they are. Yeah, I think so. Wait, there was someone else here just now. Right, okay. Okay, we are gonna check this person out. They're building a robotics simulator. So we're gonna go hang out there for a bit, and yeah, we're gonna end the stream here. That's gonna be it for today's stream. I need to continue reading up on this, and for the next couple of hours, I'm just gonna continue reading up on this, asking whatever other questions I need to ask Gemini, and hopefully tomorrow. I said this yesterday as well, but yeah, hopefully tomorrow, we will be able to do more practical stuff. I mean, I'm not really complaining because there's a reason why I keep asking these questions and I keep trying to learn and get all the information before we jump into doing something practically. There's a reason for that. It's so that I can understand what I'm doing before I do it. But yeah, that's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.